this time. Thank you very much for Ron Levie from Technium in the Israel Institute of Technology. I'm very happy to have this lecture today about Szemerédi's regularity lemma in graph machine learning. Thank you, Ron.
Yeah. Thank you for the invitation to this very interesting conference. So I'm going to show you how we can use the graph regularity lemma in graph machine learning. So we are going to show that the weak regularity lemma leads to generalization theorems of message passing networks and also sampling theorems. I'm also going to mention universal approximation. And then I'm going to show you how the lemma leads to a practical architecture of a graph machine learning model. And for these things, we are going to introduce new variants of the regularity lemma, which are appropriate for graph machine learning. Okay, and the different parts in this talk are from works with my collaborators. Okay, so we know that traditional neural networks, like convolution networks, are mappings from points in a Euclidean space to points in a Euclidean space. For example, images to labels. Now, often the data is not given as a point in a Euclidean space, but it is graph structured, and this is why we need graph neural networks. For example, in chemistry, molecules can be represented as graphs, where the nodes are represent atoms and the edges are chemical bonds. And social networks can be described as graphs, where the nodes are people and the edges are friendship, for example, any social interaction. Yeah, and we also assume that there is a feature in each node, right? For example, in a social network, the features can be the age, the number of hours the user is spending online, and so on, or the hobbies and so on. Okay, so we call this a graph signal. Okay, there are many applications of graph machine learning. Now we want to analyze graph neural networks, and if you compare the situation to the standard neural network case, where the neural network is a mapping from vectors to vectors, here we have a regular structure on the input space. Namely, we have a metric, the Euclidean metric. And using the metric properties, you can prove results like universal approximation, which says that any continuous function can be approximated by a neural network. Or generalization theorems that say that if you train the neural network on your training set, and you have a small loss, then you're guaranteed to have a small loss also in the test set. And to derive such theory, you use the metric properties of the input space. For example, you use compactness, covering number, continuity, or Lipschitz continuity of the neural networks, and so on. Now, if you go back to our case of a graph neural network, the challenge here is that the input space is quote unquote unstructured, right? Because graphs can be of different sizes and different topologies. So it is not clear how to define a metric in the input space. So the goal in the first part of this talk is to construct a useful metric on the space of graph signals that has the following properties. First of all, the metric should give a meaningful notion of graph signal similarity that makes sense in real life, namely graphs that intuitively describe the same phenomena are supposed to be close to each other in this metric. And then the metric should also have good properties. We are going to derive a metric which gives a compact space, and we are going to show that graph neural networks are Lipschitz continuous over this metric. And the compactness together with the Lipschitz continuity allow us to prove things like generalization, universal approximation, expressivity, sampling, and more. And then I'm going to show you a practical application of the regularity lemma. So if you think about it, building a metric which is both compact and that a set of functions that I'm interested in are ellipsis continuous, these are two competing requirements, right? Because to be compact, everything, all of the points in the space are supposed to be as close to each other in a sense. But the closer the points are to each other, the more difficult it is to be continuous. And the space of functions I'm interested in is predefined. It's not defined with respect to the metric that I construct. Okay, so just to make sure we all know what we're talking about, let me give you an introduction to message passing network. I know that you already saw it in the first lecture, but just to make sure, let's go over it again. So the most, probably the most well-used or the most practical architecture of graph neural network is a message passing network. So most examples of architectures that are used in practice are either special cases of message passing or slight extensions. So in a message passing network, the input space are graphs with node features. So let's consider this graph and let's represent the node features by different colors. And in a message passing network, we update the features of the different nodes layer by layer. So in each layer, we consider a message function, which is a trainable function. So let's suppose I want to update the feature value of this node. The message function is a function that takes the feature of the node that I want to update and a feature of the neighbor. And I think about the output of the message function as a message sent from the neighbor to the central node. So I apply this message function on all of the neighbors. These are messages sent to the central node, and then the central node needs to aggregate all of this information. So for example, we can sum up all of the messages or average them or take the pointwise max. The only important thing is we want an operation which is invariant to permutations because there is no natural ordering of the nodes in the neighborhood. Okay, and we apply the same message function to all of the neighborhoods. And then this aggregated message is plugged into another trainable function called the update function, which takes in the previous value of the central node and the aggregated message. And this is going to be the next feature value in the next layer. And each layer has a different trainable message function and update function. So this is what a message passing network. At the end, we can output one vector. We can aggregate the information from all of the graph. For example, we can average all of the features, or we can take the pointwise max. And then we can solve some task. We can, for example, do graph classification. Okay, so we are going to focus on normalized sum aggregation. So what you do is you sum up all of the messages from the neighbors and divide by the total number of nodes, the degree of the graph. So this is what we're going to focus on in the first part of the talk. Okay, so our goal is to construct a metric between graph signals. And the metric is going to have the following interpretation. Two graph signals are going to be close to each other if and only if they look like they were sampled from the same stochastic block model. So what is a stochastic block model? This is a generative model of random graphs where you consider a set of classes and you consider the probability of having an edge between each pair of classes and each class in itself. And then you generate a random graph by sampling nodes from the different communities and connecting each pair of nodes according to the probability that comes from the stochastic block model. Okay, so the graph is a random variable, and you can sample graphs of different sizes from the same stochastic block model. Okay, so in our metric, these two graphs are going to be close to each other because they look like they came from the same stochastic block model. Now, I can tell you that this picture, these are two random graphs. But because it's only a picture, I can also tell you that these are two deterministic graphs. Right? Even though these are deterministic graphs, they look like they were sampled from the stochastic block model. Okay, so there is a definition that tells you that quantifies how much a deterministic graph looks like it was sampled from a stochastic block model. This is called irregularity. I'm going to show it to you soon. And you can ask the following question. Is it always possible for any graph to find a stochastic block model such that the graph looks like it was sampled from the stochastic block model? Okay, and the answer to this question is yes. This is exactly Szemerédi's regularity lemma. The lemma says that for any graph, I can partition the nodes to classes such that, and build a stochastic block model such that the graph looks like it was sampled from the stochastic block model. And the important part here is that the number of classes don't depend on the graph itself, and not even the size of the graph. The number of classes only depends on how much I want the graph to look random. Okay, the more I want it to look random, the more classes I need. Okay, so Szemerédi proved this lemma in 75 for bipartite graphs, and then extended the proof to general graph in 78. And the lemma has many different variants and many different proof techniques. For example, Noga Alon et al. Proved the first constructive, gave the first constructive proof with an algorithm for computing the classes, the partition. And the lemma also has many applications in pure mathematics. So I want to walk you through one variant of the lemma called the weak regularity lemma, which was proven in 99 by Fritz and Kanan, because it's an interesting lemma and it's important for this talk. So let's go in detail on exactly what the lemma says. Okay, so what we want to do is we want to somehow compute statistics or compute densities of edges between pairs of node sets. So we need to derive some definitions. So given a graph G, let's denote the node set by V. For any two sets of nodes, e.g. US denotes the number of edges between nodes in U and nodes in S. Okay, now let's suppose somebody gave us a partition of the nodes to non-intersect, to disjoint classes V1 to Vk. Then if I focus on this specific partition, the stochastic block model that best explains the graph is the stochastic block model in which the probability of having an edge between class Vi and class Vj is the edge density, right? The number of edges between Vi and Vj divided by the total maximal possible number of edges. Okay, now the graph is deterministic. It wasn't sampled from this stochastic block model. But if the graph was sampled from this stochastic block model, we could have computed the expected number of edges between each pair of node sets. Okay, so if the graph is randomly sampled from this stochastic block model, for each two sets of nodes, U and S, the expected number of edges between U and S can be computed by this formula. You need to go over all of the blocks, all of the pairs of classes, count how many points in U, how many nodes in U you have in Vi, how many nodes in S you have in Vj, and multiply it and multiply by the density. Okay, now the graph is deterministic. So what we can do is the actual number of edges is not equal to the expected number of edges, but we can compare these two numbers, and the closer they are to each other, the more we say that the graph looks random. This is a way to quantify how random like the graph. And this definition is called irregularity, which actually measures how much the graph doesn't look random. Yeah, so the irregularity of the graph with respect to the partition Vj is the maximum over the cut, or the maximum over two sets of nodes of the difference between the actual number of edges between U and S and the expected number of edges if the graph was random. Okay, so this quantifies how much the graph looks random. And then the weak regularity lemma says that we can always choose the classes such that irregularity is small, right? And then the number of classes don't depend on the graph, only on how much I want irregularity to be small. This is the weak lemma. It says that for every epsilon, which is going to be the bound on irregularity, and for every graph, there is a partition of the nodes to classes where the number of classes only depends on epsilon, such that irregularity is less than epsilon. Okay? So in summary, the lemma says that even though large graphs look complicated, they're actually simple, and they look like they were sampled from stochastic block models. They look random. Okay, so we want to build a metric based on this, on irregularity. The metric should be such that two graphs that were sampled from the same stochastic block model are going to be close to each other. So we need to extend the regularity lemma to graphs with features, because in graph machine learning, we care about graphs with node features. Okay, so the first extension we want to make to the weak regularity lemma is to add features to the nodes. And another extension, which is actually already well known, is so eventually we want our metric to give a compact space. Now, if we only work with graphs, then the space is not going to be complete. And then if we take the completion of the space, we need to talk about all of the limit objects of graphs, and these are going to be graphons. So we want to extend the lemma also to graphons. So what is a graphon? A graphon is a limit object of a graph. You can think about it as a graph with a continuous node set, or more accurately, the node set is a atomless standard probability space. And because all of these spaces are equivalent to 0 to 1, then we can just index the nodes as the interval 0 to 1. So a graphon is you can think about it as an adjacency matrix, a continuous version of an adjacency matrix, where WXY is the probability of having an edge between node X and node Y in 0, 1. Okay, and
do you mean W in that first line instead of 0, 1, sampling a unit XM from W?
Can you repeat that? I couldn't hear.
I know, sorry. Oh,
What?
sorry. No, sorry.
It's fine?
It's
Okay.
okay. Yeah.
Okay, so another way of thinking about graphons is as generative models of graphs. So basically, they extend the idea of a stochastic block model. A random graph is generated from a graphon by uniformly sampling nodes from the node set 0 to 1, and then connecting each pair of nodes with probability that comes from the graphon, the edge weight. Another thing we need to know about.
Yeah. I do have a question. Why don't you replace the first 0, 1 and that's 0, 1 squared? Why don't you replace that by just some other probability space?
You can, but because all okay, so we are only going to assume measure theoretic properties on W. We're never going to use the topology of 0 to 1. W is never going to be continuous. It's only going to be measurable. And because it's measurable, we only care about the measure properties of 0 to 1 as a probability space. And as a probability space, it's equivalent to many other probability spaces. For example, any Polish space and so on, compact manifolds and so on. So this is why we just limit ourselves to 0, 1, because it's very general as a probability space, not as a topological space. But we don't care about topology. W is only assumed to be measurable. Okay? So you can replace it by any other reasonable space you like, and the theory applies as is. Okay? Okay. So another thing that I want to mention is that we can see graphs as special cases of graphons. So given a graph, you can take the adjacency matrix of the graph and extend it as a piecewise constant function over 0, 1 squared, and this is called the induced graphon. This is the graphon induced from the graph. So anything that we prove, we don't distinguish between graphs and their induced graphons, and anything that we prove for graphons is going to be immediately also true for graphs as a special case. Okay, so now we want to extend the notion of irregularity from graphs to graphons. And it turns out that for graphons, also for graphs, irregularity is a special case of a norm called cut distance. So for two graphons, the cut norm of the difference between the two graphons is defined to be the supermum over all of the cuts, or over all of the measurable subsets of the nodes. And you integrate the edge weights of the first graphon minus the edge weights of the second graphon. Okay, so cut distance is a way of saying how different the densities of the edges are between the two graphs. Now, if you take W1 as a graphon induced from a stochastic block model, and W2 as a graphon induced from a graph, then this is this cut norm of the difference between W1 and W2 is exactly equal to irregularity. Okay, so this extends the notion of irregularity, and this is why the cut norm inherits the interpretation also of irregularity. We can think about the cut norm of the difference between two graphons as how much the two graphons look like they were sampled from the same model. So it has a probabilistic interpretation. Okay, so for us, we are interested in graphs with signals, graphs with node features. So we want to extend the cut norm to graphons with signals. Now a signal is going to be a mapping from the node set 01 to R or to some RD. And we define the cut norm of the difference between the two graphon signals as the sum of the cut norm between the graphons plus the cut norm of the difference between the signals. Okay, so to define cut norm between signals, you take supermum over only one set of nodes. And you can show that this norm is actually equivalent to L1. It is bounded by L1 and bounded from below by 0.5 L1. But the graphon cut norm is not equivalent to any LP norm. Okay, so one last thing we want to do before we write the regularity lemma is that we want all of the analysis to be up to permutation because there is no natural ordering of the nodes of a graph, right? So we define the cut distance between two graphon signals as the cut norm of the difference between the two graphon signals up to the best permutation. And here, because the node set is a measure space, permutation is modeled as a measure preserving bijection. Okay, so you find the measure preserving bijection that aligns the two graphon signals the most, and then you take the cut norm of the difference, and this is what we call cut distance between the two graphon signals. And because we extended the notion of irregularity, we also inherit the interpretation. The cut distance between two graphon signals can be interpreted as how much they look like they were sampled from the same model of a graph signal. Okay, so now we can extend the weak regularity lemma from graphs to graphon signals. So there is already an extension to graphons by Lovas, and we add the signal also because this is important for graph machine learning. The lemma says now that for every graphon signal and every epsilon, this is going to be a bound on the cut distance. There exists a piecewise constant graphon signal, namely a stochastic block model, such that the cut distance between the graphon signal and the stochastic block model is bounded by epsilon. Now, the important thing here, again, the number of blocks only depend on the error tolerance. But here, because all of the analysis is up to permutation, we can actually choose the classes to be the intervals, the interval equipartition, right? Because we can always sort the partition to be intervals because everything is up to permutation. So if you think about it, this means that we approximated the space of graphon signals, which is infinite dimensional, by a finite dimensional space, because the partition is fixed. And from this, you can prove compactness. But before I show you compactness, by the way, this bound is essentially tight. You can, if you reduce this 2.01 to something smaller, you can show that there is a graphon signal such that there is no stochastic block model with less than this number of blocks that approximates it. Okay, so let me give you an illustration for the theorem. So this is the graphon signal. The graphon is, so this is 0, 1 squared. The edge weights are in grayscale, and the signal is plotted on the diagonal in color. And the lemma says that there is always a permutation that brings the graphon signals to a form that can be approximated by a stochastic block model. Right? And obviously, I exaggerated here the situation, but the lemma says that this is always possible. It's always possible to do that. Okay, so as I explained before, using the regularity lemma, we can prove that the space of graphon signals with cut norm is compact. Okay, not only is it compact, we can also bound the covering number. Okay, so if we want to cover the whole space with balls of radius epsilon, we know how many balls. At most, these many balls. So that if you think about it, what we showed is that the space of all graph signals, which looks like a huge space, right? Because graphs can be of any size, so it's definitely not finite dimensional. It's actually dense in a small space, in a compact space. Okay, but this is still not useful for us unless we can show that the functions we are interested in, the message passing networks, are Lipschitz continuous, right? Because we can always construct a space which is very compact, for example, a trivial metric, and then obviously the space is small, but our functions are not going to be continuous. Okay, so the next thing that we want to check, we want to verify that message passing networks are Lipschitz continuous with respect to cut norm. Sorry, with respect to cut distance. Okay, so before we do that, because we extended the analysis from graph signals to graphon signals, we also need to extend message passing networks to graphon signals. Okay, so to extend the message function, this is actually trivial because the message function takes the feature of the central node that I want to update and a feature of the neighbor. And the message function doesn't care about the topology, right? That doesn't care about the set of all other nodes. Right? It operates pairwise. So there's nothing to extend here. The only thing we need to extend is the aggregation, how to collect all of the messages from all of the neighbors. And the natural idea here is to extend some aggregation to integral aggregation, right? To aggregate all of the messages Q to the point X, you need to integrate them against the edge weights. Right? And you can show, it's easy to see that in the special case where the graphon is induced from a graph, right? It's a piecewise constant graphon that comes from a graph, then this integral aggregation is normalized sum aggregation. So this extends the standard message passing networks in a natural way. Okay, so now you can prove that message passing networks are Lipschitz continuous in cut distance. Namely, if you have two graphon signals and you plug them in a message passing network theta, and you compute the distance between the two outputs, this is bounded by the distance between the two inputs up to a constant, right, the Lipschitz constant, which is guaranteed to exist. And the only thing you need to assume here is that the message functions are Lipschitz continuous. If they are Lipschitz, then you are guaranteed that this L exists. Okay, so now we know that we have a compact space, and we know we have a bound on the covering number of the space. On the other hand, the functions we are interested in, message passing networks, are Lipschitz continuous, and the compactness plus Lipschitz continuity leads to many nice results. You can prove a generalization theorem that says that if you train a network on a training set, then the loss on the test set is guaranteed to be close to the loss in the training set. The nice thing here is that you don't need to assume anything on the data distribution. Right? The distribution from which you sample the training set can be any Borel probability. If you compare it to other generalization bounds of graph neural networks, they always need assumptions on the architecture or assumptions on the probability on the distribution of the data, and we don't need any of that.
Can I ask you a question? Are you
Yes.
saying something about the convergence of gradient descent in this theorem?
No, it's not about convergence, it's about generalization. Basically, what we say is that it doesn't matter how you got to the neural network, to the graph neural network. What matters is that the graph neural network depends on the training set. Okay, in the situation where you have a graph neural network which depends on the random training set, you are guaranteed, and then you can compute the accuracy on this training set. This is called the empirical risk. You're guaranteed that the average accuracy on any other graph sampled from the same probability distribution is close to the accuracy on the training set. Okay, so it's not a theorem about convergence. This is called uniform generalization, or it's called uniform convergence, but not the same type of convergence as convergence in gradient descent. If you want, I can show you after the talk some slides that explain the setting here. Okay, we can also prove a sampling theorem that says that if you have a large graph.
I'm sorry, Ron. I think there is another question.
Ron,
Okay, yeah.
question about it. So you are trying to make some fit distribution in the another graphs or something like that to see if they're coming from some fit distribution or something like that for the graphs.
The setting is as follows. This is a typical setting in statistical learning. You have the data, and you want to treat the data as generated from some stochastic process. Okay, so we have a probability space, and you assume that each point in the data set is sampled randomly from this probability space. For us, the probability space is a probability space over all graph signals. And what I'm saying is that it doesn't matter what this probability space is. Obviously, it has to be Borel, right? So we can analyze it using measure theory. But for any probability space, the generalization theorem applies. So it doesn't matter what type of data you have. You always have a guarantee about that the average accuracy outside the training set is close to the average accuracy inside the training set. And the distance between them goes to 0 as the training set increases. This is similar to Monte Carlo analysis. But the more data you sample, and you somehow compute your accuracy by summing over the data that you sampled, right? So this sum approximates an integral over all possible data.
Okay.
It's similar to the central limit theorem or the law of large numbers. The difference is that the integrand, the variable that you integrate, depends on the samples, because you sampled, when you generate the training set, you sample points from the probability space, and then the message function, message passing network depends on the sample. So it's not, so it's a bit more complicated than the law of large numbers.
Okay.
I have also a very quick question.
Yeah.
So here in your generalization theorem, this assumes that you're testing on something that has the same probability distribution as the trained sample.
Yes.
It's not only the same space; it also has the same probability distribution. If you have something that has It's obviously on the same space, but slightly different probability distribution. Can you still say something?
Not with this theory. Yeah, for this theory, you sample the training set and the test set exactly from the same probability distribution. There are analyses that consider probability shifts, like shifting, like the test distribution is different from the train distribution. But I didn't deal with this situation.
Thanks a lot.
Okay. And then you can also prove generalization theory, universal approximation. Wait, did I talk about the sampling theorem? I think not, right? But suppose you have a message passing network and you have a very large graph. What you can show is that if you subsample the graph by randomly sampling the nodes and considering the subgraph, then applying the message passing network on the small graph approximates the message passing network on the large graph. This also follows from the regularity lemma. And you can also formalize some universal approximation theorem that says that any continuous function can be approximated by a message passing network, but you need to relax the metric here. So cut norm is not the right metric to use for this theorem. Okay. Any questions about this part? Now I want to show you how we can use the regularity lemma to derive a practical algorithm for processing graphs. Okay, so what we saw until now is what we can do with the regularity lemma in order to analyze well-known architectures, message passing networks. So this is nice, but now I want to derive new numerical methods from the regularity lemma. What is the motivation? The motivation is that often we work with very large graphs. For example, a social network can have hundreds of millions of nodes or billions of nodes and 1,000 times that edges. So there is no way to fit so many edges into GPU memory when we train a message passing network. And practical methods consider sophisticated ways to subsample the graph when we train it. Now, if you think about it, the regularity lemma says that there are no large graphs. Every large graph can be approximated by a small one. It doesn't matter how large it is, right? Because the regularity lemma doesn't depend on the number of nodes. So this motivates us to somehow use the regularity lemma to somehow utilize the partition from the regularity lemma, the partition to communities in such a way that we can process the community structure, the class structure of the sets of nodes instead of the graph itself. Okay, so that's the idea, but there are a couple of challenges here. First of all, the weak regularity lemma is not constructive. So the first paper by Fries and Cannon did propose an algorithm for finding the partition of the graph, but it's not practical. It's exponentially slow in the number of nodes, and we want something that actually works in practice. And the second challenge is that the asymptotics is really bad in the regularity lemma. So if we want to approximate a graph up to error epsilon, the number of classes that we need to use is 2 to the power of 1 divided by epsilon squared, which is huge for moderately small epsilon. So it's not practical. Okay, so we want to address these two issues. So for the second issue, it's actually well known that if you allow the communities to overlap, to have intersections, then the number of communities needed to approximate the graph up to error epsilon is actually 1 divided by epsilon squared instead of 2 to this power. Okay, this is actually a part of the proof of the weak regularity lemma. As part of the proof, you first of all prove the existence of overlapping communities, and then you take all of the overlaps, and this is why you get 2 to the power of 1 divided by epsilon squared. Okay, so we need to work now with intersecting community graph signals. So these are graph signals such that we have a sets of nodes, uj, we take the characteristic function of each set and build a rank 1 matrix, right? This is the matrix that is only, it's diagonally localized around the community. And then we take linear combinations of these communities, and this is how we define an intersecting community graph. And the intersecting community signal is a linear combination of the same communities. Okay? And now you can see from this picture, for example, we have here a graph. This is the adjacency matrix of the graph. All of the edge weights are either 0 or 1, so it's very granular. We can approximate this graph with only 5 communities, which overlap. You see, these different communities overlap. This is the community times itself, a tensor product. Okay, I see there are some questions in the chat. No, not for me. Okay, so so what we want to do is, given a graph signal, we want to optimize the intersecting community graph signal that best approximates it in cut norm. So first of all, we want to relax the hard indicators to soft indicators so we can do some optimization, continuous optimization. Okay, so instead of a hard indicator that describes the affiliation of each node to the community, right? Instead of saying if the node has value 1, it is affiliated with the community, and if the node has value 0, it is not affiliated, we relax it to have affiliations between 0 and 1 that tells us how much the node is affiliated with the community instead of is it affiliated. Okay, and then so we relax the intersecting community graph signal to a soft intersecting community graph signal, which has the same structure, which is like tensor products of the affiliation functions, and then linear combination of these. Okay. Okay, so for us, a soft affiliation model is any set of functions from the set of nodes of the graph to R that contain the indicators. And then we denote by QK the set of all intersecting community graphs, which are basically the linear combinations of these rank 1 community graph signals. Okay, so it is well known that, at least for hard alignments, the number of communities that you need to use in order to approximate a graph up to R epsilon only depends on epsilon and not on the size of the graph. But this is only true for dense graphs. What do I mean by that? What I mean is that if you consider the cut norm, we defined cut norm for graphons. But then you can apply it on induced graphons, which are induced from graphs. And this gives you, as a special case, the definition of cut norm on a matrix, or adjacency matrix, right? The cut norm is the supermum over all of the pairs of sets of nodes of the sum of the weights, and you need to divide by the number of nodes squared. This just comes from the fact that you integrate, and the more nodes you have, the smaller the intervals when you induce a graphon from the graph. Okay, so the regularity lemma is true, right? The number of classes only depends on epsilon. However, cut distance is not meaningful if the graph is sparse. So if the graph is sparse, if the number of non-zero edges, the non-zero weights of edges is small in comparison to n squared, then cut distance is going to be small regardless of the entries, right? Because you only have the number of summands here is of order of the number of edges. And if the number of edges is much smaller than n squared, this is always going to be small. So what we want to do is we want to normalize differently the cut norm for sparse graphs. And then in the regularity lemma, the number of classes is going to depend on the size of the graph. Okay, so what we do, instead of dividing by n squared, we divide by the number of edges, or some number which is proportional to the number of edges, or a number which is the number of edges that we expect to see in the graph. Okay, and for the cut norm of the signal, we don't need to normalize in any special way because signals are not assumed to be sparse. Okay, and we define, okay, when we define the Frobenius norm of a matrix signal, we normalize by E the number of edges, the graph part, and by the number of nodes, the signal part. D here is the number of channels, the dimension of the features. Okay, so now I can formulate a new variant of the weak regularity lemma, which is constructive in a sense. It gives us a way to compute the communities, which is practical. Okay, the lemma says the following thing. We have, given a graph signal, A is the adjacency matrix of the graph, and S is the signal. We want to find a intersecting community graph signal, C star, P star, that approximates AS in cut norm. And we know that from the regularity lemma, the bound should be square root of 1 divided by the number of communities. Okay, just ignore for a second this term. If the graph is dense, then E is proportional to n squared, and this is a constant. Okay, so here we have a bound which is roughly the same as in the regularity lemma. And now the lemma says that, okay, we don't want to directly optimize the cut norm because computing the cut norm is NP hard. And if you think about it from a numerical analysis point of view, computing the cut norm involves a maximization process, right? Because the cut norm is the maximum over all of the cuts of something. And then we want to minimize this. So we're going to end up with a min-max problem, which doesn't work well in practice. It's not stable. What the theorem says is that we can actually minimize the Frobenius norm. We can ignore the cut norm in practice and minimize the Frobenius error between the intersecting community graph signal and our target graph signal. And if we manage to achieve a close to optimal error in Frobenius error, we are guaranteed that the error in cut distance behaves like 1 divided by k square root. Okay, I just want to stress that the optimal error in Frobenius norm is not going to be small because we are trying to approximate a very granular matrix by a low-rank matrix. And there is no way to make this small. So even though the Frobenius norm is large, if we minimize it, we are guaranteed to have a small cut distance. Okay, and minimizing the Frobenius norm is much more easy. You can utilize eigendecomposition algorithms like Langshaw's algorithm, and you can do gradient descent. Right? This behaves very nicely. So we derived an algorithm for minimizing the Frobenius norm that takes order of the number of edges in each iteration. Okay, and then given a very large graph, as a pre-computation, you approximate it by an intersecting community graph signal. Okay, and then when you want to solve the machine learning problem, for example, you want to do node classification, or you want to do prediction in some on some graph where the features change over time, then when you train the network and when you optimize the hyperparameter and when you search for a network, each iteration takes order of the number of nodes instead of order of the number of edges, which is much more efficient. And this typically you can fit in the GPU memory in cases where you cannot fit E. Okay, so here we have, for example, right, so we developed this signal processing pipeline that takes order of n operations. This plot shows you in the x-axis, you have a traditional message passing network. You have the runtime on different graphs. On the y-axis, you have the runtime of our method, the intersecting community graph neural network, and you can see a square root correspondence. These are dense graphs. Right? For dense graphs, message passing networks takes order of the number of edges. So it's order of number of n squared, and we take order of number of nodes. Okay, so I'm going to finish. I just need 1 more minute. I'm not going to show you the numerical results, but we took well-known benchmarks of large graphs. And basically, we are comparable to state-of-the-art. We are as accurate or a bit more accurate than state-of-the-art, or a bit less accurate than state-of-the-art. But we have the benefit of being very scalable to large graphs. So these are some benchmarks on node classification, and these are spatial temporal graphs. These are situations where you have one fixed graph, and you have, for example, in traffic prediction, you have a graph that represents a road system, and you have features that represent the traffic, how many cars there are at each location in each road, and you want to predict the traffic in the next time step if you know the previous time step. In such a situation, you need to compute the intersecting community graph only once as a pre-computation step, and then you can project all of the signals in order of n operations, and you can then train the neural network very efficiently. Okay, so in summary, I showed you that even though deterministic large graphs may appear to be complicated, they're actually simple, and they look like they were sampled from stochastic block models. The graph on signal cut distance is derived from this observation. It gives a compact metric space, and message passing networks are Lipschitz continuous with respect to this metric, and from this you can prove generalization theorems and sampling and more. And you can also derive new methods from this observation. And for all of these things, we extended the weak regularity lemma to different settings. One theorem is a theorem where you have a target that you can numerically estimate, and another theorem is extension to graphones with a signal. Okay, so if you're interested in this topic, you can take a look at my different my different papers on this subject. Okay, thank you.